Okay, we're now in section 15.5, Conductors and Electrostatic Equilibrium. Let's get to the PowerPoint. All right. When no net motion or charge occurs within a conductor, we say the conductor is in electrostatic equilibrium. An isolated conductor has four different properties. The electric field is zero everywhere inside the conducting material. We can understand property one by thinking about what would happen if it were not true. If there were an electric field inside a conductor, the free charge there would move and a flow of charge or current would be created. If there were a net movement of charge, the conductor would no longer be in electrostatic equilibrium. The next property is any excess charge on an isolated conductor resides entirely on its surface. Property 2 is a direct result of the 1 over r squared repulsion between the like charges described by Coulomb's law. If by some means an excess of charge is placed inside a conductor, the repulsive forces between the like charges push them as far apart as possible, causing them to quickly migrate to the surface. Number 3, the electric field just outside a charged conductor is perpendicular to the conductor's surface. We can understand property 3 by again considering what would happen if it were not true. If the electric field in the figure isn't perpendicular to the surface, it would have a component along the surface, which would cause the free charges of the conductor to move to the left in the figure. If the charge moves, a current is created and the conductor is not in electrostatic equilibrium. That means E must be perpendicular to the surface. Okay, number 4, on an irregularly shaped conductor, the charge accumulates at sharp points where the radius of curvature of the surface is smallest. To see why property 4 must be true, consider the figure on the left, which shows a conductor that is fairly flat at one end and relatively pointed at the other. Any excess charge placed on the object moves to its surface. The middle figure shows the forces between two charges at the flatter end of the object. These forces are predominantly directed parallel to the surface. So the charges move apart until repulsive forces from other nearby charges establish an equilibrium. At the sharp end, the forces of repulsion between two charges are directed predominantly away from the surface, as in the figure on the right. As a result, there is less tendency for the charges to move apart from the surface here, and the amount of charge per unit area is greater than at the flat end. The cumulative effect at the sharp end produces a large resultant force directed away from the surface that can be large enough to cause charges to leap from the surface to the surrounding air. We know from experiment that the net charge on a conductor resides on its surface. One such experiment was first performed by Michael Faraday and is referred to as Faraday's ice pail experiment. Faraday lowered a negatively charged metal ball at the end of a silk thread. This silk thread was an insulator, into an uncharged hollow conductor insulated from the ground. A metal ice pail was placed in the top left figure. As the ball entered the pail, the needle on the electrometer attached to the outer surface of the pail was observed to deflect. An electrometer is a device used to measure charge. The needle deflected because the charged ball induced a positive charge on the inner wall of the pail, which left an equal negative charge on the outer wall, as you can see in the top right figure. Faraday next touched the inner surface of the pail with a ball and noted that the deflection of the needle did not change, either when the ball touched the inner surface of the pail, as in the bottom left figure, or when it was removed, as in the bottom right figure. He also found that the ball was now uncharged because when it touched the inside of the pail, the excess negative charge on the ball had been drawn off, neutralizing the induced positive charge on the inner surface of the pail. In this way, Faraday discovered the useful result that all the excess charge on an object can be transferred to an already charged metal shell if the object is touched to the inside of the shell. This result is the principle of operation of the Van de Graaff generator, which we'll talk about later. Faraday concluded that because the deflection of the needle and the electrometer didn't change when the charged ball touched the inside of the pail, the positive charge induced on the inside surface of the pail was just enough to neutralize the negative charge on the ball. As a result of his investigations, he concluded that a charged object suspended inside a metal container rearranged the charge on the container so that the sign of the charge on its inside surface was opposite the sign of the charge on the suspended object. This produced a charge on the outside surface of the container of the same sign as that of the suspended object. Faraday also found that if the electrometer was connected to the inside surface of the pail after the experiment had been run, the needle showed no deflection. That means the excess charge acquired by the pail when contact was made between ball and pail appeared on the outer surface of the pail. What you see in the photograph is a lightning rod. If a metal rod having sharp points is attached to a house or other building, most of the charge on the house passes through these points, which eliminates the induced charge on the house produced by storm clouds. Also, a lightning discharge striking the house passes through the metal rod and is safely carried to the ground through wires leading from the rod to the earth. Benjamin Franklin first developed these lightning rods. Some European countries couldn't accept the fact that such a worthwhile idea would have originated in the New World, so they improved the design by eliminating the sharp points. Okay, next, we're going to talk about the Millikan drop experiment. It's a single slide discussion.